So, I want to do a little refresh. I know that we ended with like electron configuration and periodic properties, but in order to do today's lesson, we need to refresh on valence electrons. So if you don't remember, I need you to remember now. Your alkali metal family has one, and then hydrogen also. Hydrogen's not an alkali metal, but it's lined up because it has one valence electron. Your alkaline earth metals have two. Your boron family has three. Carbon family has four. Nitrogen family has five. Oxygen family has six. Halogen family has seven. Noble gases have eight, except for helium has two. Okay, so that's the pattern. This is how many valence electrons everything has. So we need to remember that, so what we'll do is we'll be drawing dots around certain elements. So sodium has one valence electron, so they drew sodium with one dot, right? One valence electron, one dot. Now chlorine has seven, so they drew seven around it. Okay. And now chlorine has a really, really high electronegativity. And because it has a high electronegativity, it actually is so electronegative that it will take sodium's electron, okay? And when it does, it completes its what we know as its octet of electrons, 2, 4, 6, 8 electrons, and it becomes -1 because it gained an electron. Now sodium has really low electronegativity. It also has low ionization energy. So it's like, fine, you can have my electron because when it loses it, it becomes stable too. It ends up losing its outermost shell to have a full new valence shell. And when it loses it, it becomes +1. Now the +1 and -1 is what holds, or are what holds the compound together. It's an electrostatic force of the attraction between positive and negative that holds this compound together. This is known as ionic bonding, and for ionic compounds. Now, a long, long time ago when we did naming, we taught you a cheating method to recognize ionic compounds. If you don't remember it, I do want you to remember it now. Metals with nonmetals, or metals with polyatomic, was a hint that it's an ionic compound. And ionic compounds involve full transfers of electrons. One thing loses it, the other thing takes it, okay? That is not what we're going to focus on in today's lecture. Today we're going to work on covalent compounds, which are often referred to as molecular compounds. And if you don't remember, this is nonmetals with other nonmetals. All right. So if you look at the periodic table, ionic compounds involve, I'll draw in different colors, involve metals, right? All of these guys, these are all metals, yeah? And everybody under the staircase, metals with nonmetals. Okay, that's what it means to be ionic. Okay, now covalent compounds are not like that. Covalent compounds are nonmetals with themselves. So we're going to focus on these guys with themselves. And now the reason that covalent compounds are going to be forced to share electrons as opposed to transfer them is if you look over here, right? These atoms, these nonmetals, tend to have decent electronegativities, meaning each atom is fairly attracted to electrons, so neither one of them is strong enough or attracts electrons enough to be able to completely rip the electron off of the other atom, so they are forced to share. Now, remember that all elements or atoms want to do is achieve stability. So they will bond, react, they'll do whatever it takes to achieve stability. And achieving stability, for the sake of this class, is completing an octet. So for ionic compounds, they achieve stability by gaining and losing electrons. For covalent compounds, they achieve stability by sharing electrons. Again, because neither one of them is strong enough to do or form an ionic bond. So again, today, that's what we are going to be focusing on are our covalent or our molecular compounds. Now, so electrons can be transferred. Those are in ionic compounds, which is not what we're going to focus on today. But today we're going to talk about covalent compounds and the sharing of the electrons. Now, the thing is, sometimes the electrons aren't shared evenly, okay? If the two atoms share them fairly equally, the bond is called nonpolar covalent. Nonpolar means even sharing, covalent means sharing. Okay, if they're unevenly shared, meaning one atom might yank harder on the electrons that they're being forced to share. So uneven sharing is polar, and then again, covalent just means sharing. Uneven sharing. So again, this is kind of like in a covalent bond, this is like a tug of war on the electrons. So again, this is only for covalent bonds. Polar and nonpolar are only for covalent bonds. It is not for ionic bonds. So we have this little, I guess he's not little, but this sumo wrestler, and then we have, this other little guy. So in terms of the periodic table, who is the sumo wrestler? Who is the most attracted to electrons on our periodic table? Which element is it? Ooh, this is last chapter. Who is the most electronegative element on the periodic table? Who is the most attracted to electrons out of all of our elements? Fluorine, good job. So your sumo of the periodic table is fluorine. It attracts electrons more than any other element. Right next to fluorine in strength is oxygen and then nitrogen. Those are your three most electronegative elements. So what happens is even though fluorine is sometimes forced to share, it's like, yeah, well, I'm not going to share well. So it shares unevenly and creates what are known as polar bonds. So here's a chart of electronegativities. No, you don't have to memorize it. Yes, you need to know that fluorine is the most, oxygen is the second most, and nitrogen is the third most electronegative. But you don't need to memorize all of these. We'll just use them today. And so we're also going to look at calculating the changes. That's what this triangle means, changes in electronegativity or differences in electronegativity, just using basic subtraction. So when an atom is more electronegative than another atom, we draw an arrow and we point it to the more electronegative element. And it goes like this. So this gets pointed towards the more electronegative atom if there's uneven, or if one atom is way more electronegative. And then this arrow has a name. It's called a dipole or a dipole moment. And the reason that we draw it is because what happens is that bond creates a partially negative charge and a partially positive. Now, these are not full positives and full negatives, because if they were, we would be talking about ionic compounds, and we are not. We are talking about covalent compounds. So because the electrons get yanked over in one direction, it creates a dipole or a polar bond. So I'll show you what I mean. I'm going to do my best. So let's say there's two electrons that are involved in a single chemical bond. So here's my two electrons, okay? Let's say, now this is, let's do this first. Okay, let's say the two electrons are between carbon and sulfur. Now, if you go back to your electronegativities, you will notice that carbon is 2.5 and sulfur is 2.5. What does that mean? Well, that means that carbon and sulfur have very similar attractions to the electrons. Okay, so that means if carbon yanks fairly similarly to the electrons as much as sulfur does, the electrons will be pretty even in the middle of the, like in towards the center of the bond, okay? However, if the two elements that are sharing have big differences in electronegativity, for example, we know that fluorine is really, 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 really attracted to the electrons. So fluorine's like, okay, I'll share because I'm not electronegative enough to rip the electron off of hydrogen, maybe something else, but not hydrogen, but I'm still stronger. So the electrons don't exist in the middle. The electrons actually get yanked closer to fluorine. And if electrons are being pulled over here, this region of the dipole is slightly negative because electrons are negative. And then this region is slightly positive because the negative charge is leaving this area to become partially positive. So we call this a dipole moment or a polar, uneven sharing, covalent bond. Okay? So I drew these for you. This is water. okay? So oxygen is definitely more electronegative than hydrogen. So when you draw your dipoles, you point them towards the more electronegative element within the bond. There's a bond here and a bond here, okay? And then this bond, okay? So this is called, oops, I wanted to do a different color. Polar uneven sharing covalent bond. The electrons are being pulled towards the oxygen, which means this is also a polar covalent bond. You need to remember polar means uneven sharing. So the symbol that's used is the arrow. So that's the arrow, and then this is a Greek symbol. It means partial. Partially positive, partially negative. Okay? So let's look at a different molecule, sulfur dioxide. Okay? So I'll go ahead and draw. It's actually a little bit more complicated than this, but whatever. All right, so oxygen is way more electronegative than sulfur. So oxygen yanks harder on the electrons. It shares them, but it doesn't share them well. So that creates this uneven distribution of electrons, making this end partially positive towards the oxygens, and the sulfur end partially, this oxygen end is partially negative, and the sulfur end is partially positive. And then it does it for this chemical bond right here, this covalent bond. Oxygen doesn't share well, so this region becomes partially negative, and this region becomes partially positive. So this arrow is called a dipole, and it represents a polar covalent bond. So polar means uneven sharing, or uneven, and the covalent means sharing. Right? That's what co means, right? Like if you're co-captains, you both share the jobs of being a captain. So that's what covalent means. Okay, so uneven sharing creates a polar covalent bond. Uneven sharing creates another polar covalent bond. Okay, so then if you look at these three different, these are like electron densities. Okay, you don't know how to draw them yet, but I'm going to draw them for you. So fluorine, diatomic fluorine looks like this. Okay, and you'll notice this molecule, this is F2, right, has electron densities that are pretty evenly shared throughout the molecule. Why is that? Well, fluorine bonded to itself, this fluorine attracts the electrons just as much as this fluorine. They're similar in strength or similar in electronegativity. So because of the even sharing of electrons, this is a non-polar, that means even, covalent sharing. The electrons are evenly shared, so this is a non-polar covalent bond. Even sharing of electrons. Now, let's look at HF. Shoot, I know the blue's kind of hard to see. Okay. Is one of these guys more electronegative than the other? Absolutely. You better believe that the fluorine is super electronegative. It's going to attract the electrons more. So look at this red region. That's where you are finding high density of the electrons being found in the molecule at any given moment. Meaning the electrons are totally being yanked towards fluorine. So that's uneven sharing. So what do we call uneven sharing? Polar, uneven, covalent sharing. Uneven sharing. So it has a dipole moment, okay, that's pointing towards the fluorine. So this region over here is slightly negative, and this region is slightly positive. Now, look at how much worse the distribution is here with LIF. Anybody know why? Why is LIF even bigger of a distribution? Lithium is a metal, fluorine is a non-metal. So this guy is what? Is it covalent? Do you think that lithium fluoride shares electrons with each other? No way. This guy's ionic. Meaning fluorine's going to jack the electrons from lithium, and lithium's like, sweet, fine, you can have it. I don't care. Okay, lithium will lose it and fluorine will gain it. So there's no sharing going involved. Ionic compounds cannot be termed polar or nonpolar. Polar and nonpolar are specific to covalent bonds, not ionic bonds. Okay, so now we're going to do some using bond electronegativities. I'm going to prove using math. Now, what's interesting is a while back ago, so this is a metal, right? This is a non-metal. And we told you that if you see a metal with nonmetals, it's ionic, okay? Metal, non-metal, ionic. So now I'm going to prove that to you using electronegativities. So if you go look up sodium's electronegativity, it's 0.9. So if you reference back to the chart, okay, sodium's 0.9, okay, and chlorine is 3.0. So when you do electronegativity differences, there's no such thing as negative, so you just always take the bigger number and subtract the smaller number. Okay, we're calculating changes or differences in electronegativity using the chart. So what's 3 minus 0.9? Well, 2.1. Okay, this is what here, right? So it's ionic, which you already knew, but now I'm using math to prove it. Okay, what about lithium fluoride? Well, if you look up fluorine, its electronegativity is 4, minus lithium is 1. So that's what, 3? All right, ionic, which you kind of already knew because we cheated a long time ago and told you that metals with nonmetals tend to be ionic. Okay, you'll notice on different sources that some of the cutoffs might change slightly. So just use whatever cutoffs they give you on that. So if you have a worksheet and they don't call this 0.5, they call it 0.3 instead, use that cutoff that's given on that practice worksheet, okay? Some sources do have slightly different cutoffs. I'm never going to give you one that lands like right on the cutoff, okay? So now let's talk about other types. So I'm going to draw CS2. Now you don't need to yet, you will soon. But here's its Lewis structure, that's what it's called. So this is a carbon-sulfur bond right here. So I'm going to focus on just this bond, just this carbon and sulfur. So if you look up carbon, its electronegativity is 2.5. If you look up sulfur, its electronegativity is 2.5. Well, what's 2.5 minus 2.5? 0. What does that mean? This sulfur and this carbon, neither of them is like much more attracted to the electrons than the other. So they share the electrons right here fairly evenly. Even is called nonpolar, and then covalent is sharing. So this right here is a nonpolar covalent bond. Now, this is the same exact bond, okay, between carbon and sulfur. So this is also a nonpolar covalent bond. So this guy has 2 nonpolar covalent bonds. Okay, what about diatomic chlorine? Well, it's chlorine attached to itself. Okay, so this chlorine is going to yank just as hard as this chlorine. So they're going to share the electrons fairly evenly. So even sharing is called nonpolar covalent. This is a nonpolar covalent chemical bond. Okay. So water, I'm going to draw for you. Okay. Now, oxygen's electronegativity is 3.5. Okay. Hydrogen's electronegativity is 2.1. So you subtract them and you get 1.4. That's a fairly big difference in electronegativity, meaning the oxygen will attract the electrons way more than the hydrogen creating a dipole or a polar covalent bond. So this bond, right, 1.4 falls like right here in my polar region. So this bond is a polar covalent bond. So this is the same exact bond, oxygen and hydrogen. So this bond is also a polar covalent bond. All right, SO2, I'll draw for you. Okay. So now we're working with a sulfur-oxygen bond. So sulfur, its electronegativity is 2.5. Okay. Oxygen's electronegativity is 3.5. So if you subtract them, you get 1. Well, 1 definitely falls in my polar region on this chart right here. So there's uneven sharing. Now this should make sense. Oxygen's the second most electronegative element on the periodic table. So it heavily attracts electrons. So there's uneven sharing going on right here because oxygen is so attracted to the electrons. So they call that polar, uneven, covalent sharing. So this is a polar covalent bond. Now this is the same, a sulfur-oxygen bond. So this is also a polar covalent bond. Any questions about this concept before we move on to something else? So atoms can gain or lose electrons, and those are for ionic bonds. Okay, when they gain electrons, they complete their shell, and when they lose electrons, they lose their valence shell and end up having a full shell below it. So that's for ionic. Now for covalent compounds, we will complete electrons in the s and p orbitals, and it is pretty complicated in terms of like orbitals overlapping so that they can be shared. But we're going to be sharing electrons for the octet rule and our Lewis structures, meaning everything we draw today is going to be with non-metals with other non-metals. That's everything we're going to draw with Lewis structures. I will tell you that sometimes you will see metals involved in covalent bonding because all compounds can have covalent character. You see it happen a lot with really small ionic substances, but mostly we'll be focusing on non-metals with other non-metals, okay? And we're going to be sharing. So electron configuration. So let's tie this back to last chapter. Electron configuration for nitrogen. So 1s2, 2s2, 2p3. Now this right here is your highest occupied energy level, right? N equals 2. All right. So how many valence electrons are there? Well, there's 2 right here plus 3 more right here is 5. So when we draw an electron dot diagram, you write the symbol nitrogen. And then we focus on the valence electrons because those are the electrons that are furthest away from the nucleus and available for bonding. So we draw 5. Now the general pattern is to start at the top, 1, 2, 3, 4, and then you pair up. Okay, so this is the Lewis dot structure for nitrogen. Now, there's all of these rules that I'm not going to read out to you right now, but I will discuss them as we start practicing drawing Lewis structures, okay? And then I will use this wording once we start drawing Lewis structures. So I would like to practice with you to start with HCl. HCl. So the first thing you're going to want to do is figure out how many valence electrons each element can contribute to the molecule. So oops. Okay, so hydrogen has 1 valence electron, chlorine has 7 valence electrons. So that's how many electrons we have to work with. 1 and 7. 1 from the hydrogen and 1 from the chlorine. So I'm just going to draw them down here. So here's hydrogen. Here's chlorine. Now, I know I said you generally start at the top, but you'll start to get this as we practice. Hydrogen has one valence electron. I'm going to line it up because I know I'm going to probably start forming a bond. Non-metal with another non-metal, meaning they're probably going to be forced to share. So HCl. Now, I said chlorine has 7 valence electrons, so I'm going to do 1, 2, 3, 4, 5, 6, 7. Now look, you have to bond everything at least one time, or there's no point of even doing this. So let's look at this. Now, I need you to know that hydrogen does not want to bond more than one time. It can't. It can only have 2 electrons. So it's actually satisfied with what we know as a duet of electrons. Hydrogen is okay having 2, and that's actually what causes it to be stable. What that also means is hydrogen is never going to be a central atom. Like never, ever, 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 ever. It's never going to be a central atom. So that's because it can only bond one time, ever. So now let's look at chlorine. Now that they're sharing, chlorine has 2, 4, 6, 8 electrons. Oh, we've achieved an octet of electrons. So terminology-wise, this right here is called a bonding, because they're sharing, right? A bonding pair of electrons. Bonding pair of electrons. It's also referred to as a sigma or single bond. Single just means one line, also called sigma. So yes, you need to know that. Okay? Now, 1, 2, 3. These guys are called lone pairs of electrons. They're alone, like in the sense that they're not involved in a chemical bond, but they are paired up. So they have a partner, a partner, a partner. So this molecule has 3 lone pairs of electrons. This is it. This is the Lewis structure or Lewis dot structure of HCl, hydrochloric acid. Questions? Okay, we're going to try another one. Let's draw water. So water's obviously H2O. Now, in general, the least electronegative element is generally in the middle or the central atom. However, that's not always true. This is an example. Oxygen definitely is more electronegative than hydrogen, but we know we can't throw hydrogen in the middle of atoms because it can only bond one time. So you will never see hydrogen as a central atom, ever. So I'm going to throw oxygen in the middle, and then I'll put my hydrogens on each side. So let's see. Hydrogen has 1 valence electron, and there's 2 of them in the molecule. And then plus oxygen has 6 valence electrons. So I have 8 electrons to work with. So I'll give hydrogen its 1 electron. That's easy enough. And again, you're gonna get practice at this, but I'm gonna line this up, right? Because we know we're gonna have to create bonds. So I'm gonna line the hydrogen up of probably where it will bond to the oxygen. And now oxygen has 6 valence electrons. So 1, 2, 3, 4. Now, before you finish drawing, look at, you have to bond everything at least one time. So you might as well do that off the bat. But I didn't finish. I need 6. So now I can pair these guys up. 5, 6. Okay? So this molecule has 2 bonding pairs of electrons, which is also known as 2 sigma. This is the Greek symbol, lowercase, for sigma bonds, or 2 single bonds. Okay? And then these are, lone pair both of those. So this molecule has 2 lone pairs of electrons. Questions? So let's look at it. Let's look at what's achieved by sharing the electrons. Oops, I gotta go back to my... Okay. So look at around oxygen, 1, 2, 3, 4, 5, 6, 7, 8. Oxygen has achieved an octet of electrons, okay? Hydrogen has 2, and hydrogen is perfectly stable with 2. So 2, 2. They're all being shared. Maybe not evenly, but they're being shared in order to achieve stability. So last one, and then I'll let you go. So please try to draw CHI3. So carbon has 4 valence electrons. Hydrogen has 1 valence electron. Iodine has, this is an I, has 7 valence electrons, but there's 3 of them. So that gives me a total of 21 plus 1 is 22 plus 4 is 26 electrons to work with. So carbon, now how you, carbon is the most versatile element because it has 4 valence electrons. So if you see carbon in a compound, it is almost always your central atom. Okay, so that's just like another strategy. So now I'm going to, again, I kind of lined these up how I chose. So let's say you put your hydrogen over here, and then this iodine was over here. It doesn't matter, okay? Just as long as you have them all lined up around. Now carbon is 1, 2, 3, 4 valence electrons. The iodines have 7. 1, 2, 3, 4, 5, 6, 7. Now I know I'm going to bond, right? That's the whole point. 1, 2, 3, 4, 5. Now be careful. 6. Now I'm not going to pair it up right here because I know this is going to bond. 7. Okay. So 1, 2, 3, 4. I know this is going to bond, so 5, 6, 7. Okay. And how many does hydrogen have? 1, right? 1. Bond. So look at hydrogen completes the duet. Iodines 2, 4,